Hi, in the previous modules we've talked about doing single subject and group level GLM analysis. In this module we'll talk about how we can threshold the resulting statistical images, and we'll talk about the multiple comparisons problem. So to summarize what we're doing here, when we're trying to localize areas of activation, we begin by constructing a model for each voxel of the brain. We usually do this is called the massive univariate approach, and a regression model such as the GLM is commonly used. So what we would do is, for each condition, we would take the stimulus function corresponding to that condition, convolve it with the HRF, and get predicted bold responses corresponding to each condition. In this example, we have two conditions, A and B, and we see here to the right the predicted bold response for A and B. We add those as columns of a design matrix, X, as follows. So we have Y, the data, is equal to X, which is the design matrix, which contains information about the experiment. So these two predicted bold signals. We have beta, which is the parameters which weigh these predicted bold signals, plus epsilon, where epsilon is normally distributed with mean 0 and variance covariance matrix B. So we do this at each voxel of the brain. Next, we perform a statistical test to determine whether or not the task-related activation is present in the voxel. So typically we perform some tests such as testing whether or not C transpose beta is equal to 0. This is some sort of contrast. For example, in our example, we could see whether or not the beta corresponding to condition A minus the beta corresponding to condition B is equal to 0. This is equivalent to testing whether or not the betas for both conditions are the same. So we can test this by, for example, performing a t-test. And if we perform a t-test at each voxel, we can replace the fMRI time series at each voxel with summarize it using the t-statistic value. And that will give us a statistic image. So this is a map of t-tests across all voxels of the brain. The next step, and the one we haven't really discussed yet, is how do you choose an appropriate threshold for determining statistical significance? Now the T-map on the previous page gives us a heat map of what's going on, but what we ideally want to do is make a binary decision. Is this voxel significant or not? And so we have to find a value which to threshold this T-map and say that voxels that have T-statistics above that particular value, that particular threshold, are active, and ones that are below are non-active. And here we see an example of such a thresholded image. This is sometimes called a statistical parametric map. Here, each significant voxel is color-coded according to the size of its p-value. So we see here that we have three coherent regions of activation using the threshold that we used here. Now, deciding on a threshold is a difficult problem in fMRI because we're doing so many tests simultaneously. But before we go into that, let's have a quick review over the ideas behind hypothesis testing and the notation. So we usually, again, we start by stating a null hypothesis, and this is usually a statement of no effect, such as beta 1 minus beta 2 is equal to 0. That means that there's no difference between the two. And the alternative hypothesis may be that there is a significant difference, say that beta 1 is bigger than beta 2. In that case, the alternative would be that beta 1 minus beta 2 is bigger than 0. Now, in order to test the null hypothesis, we have to compute a test statistic. A test statistic measures the compatibility between the null hypothesis and the data. So we assume that the null hypothesis is true, and we see whether or not there's evidence in the data that contradicts that statement. So, for example, if we compute a t-statistic, we're seeing whether or not the sample mean is significantly different from some hypothesized mean. So if the t-statistic is small, that means that there's no incompatibility between the observed data and the null hypothesis. If the test statistic instead is very large, that means that the data is not compatible with the null hypothesis, and that might lead us to believe that the null hypothesis is not true. The p-value is the probability that a test statistic would take a value as or more extreme than that actually observed, as long as the null hypothesis is true. So for a one-sided test statistic, we see an example here on the right-hand side. We see that if our t-statistic were equal to some value t here, values that are as or more extreme than that would be t-values that take values around this axis. So the probability that such a t-statistic would occur under this null distribution would be this probability here. So what does the p-value mean? Well, that means that if the null hypothesis is true, and we get a very, very small p-value, say a p-value of 0.01, this indicates that we have observed something that would only happen 1 out of every 100 times if the null hypothesis was actually true. So then we have to decide whether or not we believe that this is sufficient evidence in order to reject the null hypothesis. Oftentimes we make this determination based on something called the significance level. So what we can do here is we can set a certain threshold, say that if the test statistic is in the, say, 5% most extreme values, then we would reject it. So there is a threshold, which I'm going to call U of alpha here, which corresponds to what that t-statistic, what value that t-statistic has to take in order to exceed and be in this region alpha of the say 5% most extreme values. So in this case, in imaging, we often perform this type of analysis. We decide a certain threshold, and we deem voxels with a test statistic above that threshold to be active, and voxels with test statistics below that threshold to be non-active. So in general, when we make binary decisions like this, that a voxel is active or not active, there's two possible errors that we can make. One is called the type 1 error. That's when the null hypothesis is true, but we mistakenly reject it. This is also called a false positive. And this is controlled by the significance level alpha, because alpha is telling us, what proportion of the times, if the null hypothesis is true, what proportion of the times would we reject it mistakenly. The other type of error that can occur is what's called a type 2 error. Here, the null hypothesis is false, but we fail to reject it. That's also called a false negative. The probability that a hypothesis test will correctly reject a false null hypothesis is sometimes called the power of the test. So we ideally want that to be very, very high. And usually we choose the alpha level to control the type 1 error, but we control the power by increasing the sample size. Now, choosing an appropriate threshold is complicated by the fact that we're dealing with a family of tests. So if more than one hypothesis test is performed, the risk of making at least one type 1 error is going to be greater than the alpha value for a single test. So for a single test, if we set the alpha value to be 0.05, then there's a 5% chance of making a type 1 error. However, if we perform more than one test, the likelihood of at least making one type 1 error is going to be greater. So the more tests one performs, the greater the likelihood of getting at least one false positive. So going back to our problem, let's say that we performed this massive unary approach. We performed a GLM analysis at 100,000 different voxels, and we want to determine which of these 100,000 voxels are significant. Let's say that we thresholded each test at an alpha level of 0.05. Well, if we do that, we're basically saying that we're going to make a type 1 error 5% of the time. In 100,000 tests, that implies that we're going to get 5,000 false positive voxels. So entire brain regions can be created based on these false positive results that will completely make us misinterpret what's going on in the brain. So in general, choosing the appropriate threshold is a balance between sensitivity, controlling the true positive rate, and specificity, the true negative rate. Here we see an example of a variety of different ways we could threshold the statistic image that we showed here on the right. If we do a very lenient threshold, a lot of voxels will be deemed active. And as we do a more stringent threshold and move to the right, fewer and fewer voxels are active. So let's take a closer look at these two extremes. If we start with the image to the left, here we have a very lenient threshold. Lots of voxels are deemed active. In this situation, we're pretty sure that we've captured all the truly active voxels. But of course, we can't shake the feeling that we've also have a lot of false positives here, voxels that we deemed active that really shouldn't be active. On the other hand, if we go to the right and we look at the more conservative threshold, in this case, we have one coherent block of activation. We might be, in this case, be very secure in the knowledge that this region is active during this task. But now we can't shake the feeling that we might have thrown out some truly active voxels because of the stringent threshold. So determining an appropriate threshold is a fine balance between finding, sensitivity and specificity. We want to find a threshold that kind of controls both of these things. And that's what a lot of these multiple comparisons approaches allow us to deal with. Now, there exist several ways of quantifying the likelihood of attaining false positive, and we have to talk about this in order to choose an appropriate threshold. Now, we can control the family-wise error rate, or the FWER, which is the probability of any false positive. So if we want to make the probability of getting any false positive of the image very, very small, we say that we control the family-wise error rate. If instead we want to control the proportion of false positives among all rejected tests, then we're controlling something called the false discovery rate. Now, depending on whether we control the family-wise error rate or the false discovery rate, this allows us to choose the threshold in a principled manner and allows us to control the number of false positives in a variety of ways. Okay, so that's the end of this module. We've talked about some of the issues that we're faced with when trying to threshold the statistical image. Now, what we want to do is we want to balance sensitivity and specificity when deciding an appropriate threshold. And so there's two criteria that we sometimes use in order to get a principled choice of threshold. That's the family-wise error rate or control the false detection rate. And so in the next couple of modules, we'll explore these two concepts. Okay, I'll see you then. Bye.